Okay, so let's pick up where we left off. Let's look back at last time. So last time we were talking about extended surfaces where we are trying to make this assumption that the resistance to conduction inside the fin in this y direction is small relative to the resistance to the surroundings. And if we can do that, then we can model this entire thing as a 1D problem. In the sense that there's a temperature gradient in x. There's a temperature gradient in this direction here, but there's no significant temperature gradient inside the domain. Okay, so we've made that assumption. Here's some plots that kind of illustrate the idea, and then we capture that the accuracy of that assumption with the BO number. All right. Today, what we're going to do is let's first start off by getting to the right page. Let's start off by thinking now about, instead of this resistance in the y direction, let's compare the resistance due to conduction in x to the resistance to the surroundings and think about some scenarios there, because that maybe helps us describe the fin in a more general way. All right, so we have these resistances. I guess they're written out here. R conduction x. So let me see here. So we have this resistance R conduction in x. This is the total resistance going in this direction, in the direction of primary heat flow. And then we have R convection, our resistance to the surroundings. So I want you to think about what happens in a case where R conduction X and R convection are very different from each other. So let's say this another way. Let's draw out this plot. I'm going to make this temperature. So actually, instead of temperature, let's make it a non-dimensional temperature, which would be T, the local temperature T minus T infinity over TB minus T infinity. Right, so this is going to be between 0 and 1. So down here we have 0, up here we have 1. And then let's make this the non-dimensional position, which would be X over L. So again, this would go from 0 to 1. So first, let's think about a case where the resistance to which one should we do? Let's pick the resistance to conduction is much less than the resistance to convection. So heat can really easily move in the x direction, but struggles to convect away. So what would the temperature profile look like in that case? Yes, exactly. You're going to basically have a straight line across. So it's going to look something like this, right? Which is sort of this straight line across. Maybe there's a little bit of heat loss. So this is a case where R conduction in x is much less than R convection. Let's think about the other case. What happens when R conduction x is much, much greater than R convection? How would that look? So how would the temperature profile look in the case where heat really struggles to go in the x direction, but very easily convects away? Right, it's going to go, yeah, it's going to go straight down. Right, so something like this, right? So this is our conduction in x is much, much greater than our convection. And then you can imagine all the cases in between, right? They're going to get this family of curves that kind of do this. Okay, so I'm drawing this out. One thing that I want to make clear is what happens in terms of the gradient of temperature with respect to position as you get to x over L equals 1. This fin, which is maybe not clearly stated, has an adiabatic tip. We're assuming that there's no heat flow. So my derivative of dt dx at x equals 1, or x over L equals 1, had better be 0. So all these curves that I'm drawing for this particular fin are going to have the gradient of 0 at that boundary. So this family of curves is now specific to this type of fin, but if I characterize the ratio of resistances for any given fin, I should be able to look at the temperature profile just from something like this. Okay? So this kind of gives you like the conceptual understanding that we're going to need. Now we're going to move on to actually deriving how you get to these temperature solutions, right? So we have our non-dimensional temperature, our non-dimensional position. Let's go through and figure out how we would actually get expressions for these. Okay. So here's the fin, the extended surface. We have an adiabatic tip on this. And what we want to do is come up with temperature as a function of x, right? So oops, let's do this, x. So this is our x position. So we're going to do this the same way we do all the other analytical solutions. We're going to start off by drawing a control volume. Somewhere in here, it's a differential control volume. And I'm going to now keep track of all the stuff that's going in and leaving. Sorry, this control volume extends down, right? So coming in the x direction, we have q dot x. Leaving, we have q dot at x plus dx. And then we also now have convection, right? This is different from what we've done before. We had generation in the last set of problems. We don't end this problem. We have convection away. So we're going to draw, let's just draw it leaving. So this would be q dot convection. But it's important to note that this convection is a function of position, right? It's a function of the temperature difference at that differential location. So we need to come up with expressions that reflect that, right? So there's our control volume. We do an energy balance on this. So in is going to be q dot x, and then leaving is q dot x plus dx, and q dot convection at x. Let's see. Let's expand this out. So q dot x is equal to q dot x plus dq dot x dx times dx. That's just that first term. And then we still have to bring along our q dot convection. All right, the q dot x's cancel out. And we're left with the governing differential equation in heat, which is dq dot x dx times dx is equal to minus q dot convection at x. Okay, hopefully it's clear how we have that. Again, this kind of looks like that generation case where you have some dq dot dx and it's related to something on the right-hand side. In the generation case, we would normally say this is like some constant volumetric term, or maybe it was a function of temperature as you did in the last homework. Here now, this is just the heat that's leaving. So the rate of heat flow change across a differential volume is only related to the convection heat loss. And so it's kind of a similar thing, but that convection heat loss includes temperature now. Okay, so let's keep moving on this. We need to get some rate equations introduced. So let's start with, let's see, well, let's first look at Fourier's law. So the dq dot x dx term, that's going to be Fourier's law, where q dot x is equal to minus k times the cross-sectional area of the fin times dt dx. And then our convection, q dot convection, is Newton's law of cooling. So we know it's going to be h bar, some convection coefficient. Right? So you have, like, say, didn't draw it, but up here in the diagram we have some convection that's occurring. So it's h bar times the area. What is the area that we're going to use here? So let me just give you some dimensions here. So let's draw this kind of into the page. And let's say that I have this, call that perimeter, right? Yes. So the area available for heat transfer due to convection is perimeter times dx. Now, okay, this is for a rectangular fin, right? So it's pretty easy. If you're doing a fin that doesn't have a constant cross-sectional area, you need to make sure you're using the right differential area. So if it's expanding, you need a function of area that depends on position or something like that, right? So you got to be a little bit careful about that. So okay, h bar perimeter dx times the temperature T at x minus T infinity, right? So let's say out here we have h bar and T infinity. Right, so now we have our rate equation for conduction. We have a rate equation for convection. Those just plug in directly. So this is going to go here. This is going to go here. And now we have our differential equation in terms of temperature. So let's write that out up here on top. So we have dx of minus k AC dt dx times dx is equal to the right-hand side, which is minus perimeter times dx times h bar times t. I'll just say t minus t infinity. I'm shorthanding a little. I'm just saying t, but we know t is a function of x. OK, so what can we do here? The dx goes away. The k minus kac, right, that's some constant. So let's put this in standard form, which means let's get all the constants over to the other side. And we're going to end up with our kind of simplified ODE here, which is d squared t dx squared is equal to perimeter times h bar over k ac. This is perimeter h bar over k ac times t minus t infinity. Right, the minus sign on the k cancels with the minus sign on the right-hand side. All right, so this is our ODE. Any questions on how we got that far? Yeah.
Why is that a double derivative?
So we had, let's see, up here, we have d q dot of x, but q dot itself is dt dx. So it's d dx of dt dx.